All right. I think we're live. Good morning, afternoon, evening, wherever you are. I'm Josh, Lawyer of Podlex. I work on the foundation and tend to host these developer calls. And today we've got a pretty exciting one for you about Bitcoin. We have a bit of an encore here from timluc-miptev, who did one of these calls about the Bitcoin wallet back in December when it was, still in the works. Now we're at the point where we have launched a Bitcoin wallet with the work that he did back then, with also the work of a few other contributors, some folks at Tlon, some people in the community. So all of this Bitcoin work has really come together very nicely. If you haven't seen the Bitcoin wallet, check it out. There are instructions now on urbit.org about how to install this and get it up and running. So yeah, feel free to ask some questions in the chats if you have them. We'll go ahead and field those kind of as they come today. This call is a little bit more informal. It's meant to be kind of a workshop where Tim's going to run you through how to program Bitcoin specifically from within Urbit. And this is important because our Bitcoin wallet has largely been a community effort to pull it together. Of course, it's all open source, and it's probably still going to be a community effort to keep maintaining the thing and adding some features to it. And so we have a whole bunch of issues and features to add. We keep these in a public GitHub repo that I'll link to later. And we're going to be looking for some more people to help out with this. So Tim will talk a little bit more about that later. So if you're interested, definitely reach out to us. You can do that in the comments here or on the Hangout session that we do after this. So at the top of the hour, we'll, after we finish up the developer call, we'll throw a link in. You can join, and you can just hang out and talk to us directly. So anyway, let's go ahead and bring Tim in. Hey, Tim.
Hey, am I live now?
You're live
now.
Sure,
it's on there. Everyone's seeing my screen. All right, cool. And yeah, I just want to preface this by I'll give the goal of the talk in a sec. If you know Bitcoin programming really well, down to kind of the very mechanical byte level and how everything works, there may well be a point where you know something in here better than I do. Because a big point of this talk is that I'm pretty much completely self-taught in this and just had to pull together a lot of resources on the internet to do the wallet and then to start helping manage the Lightning grant. Because they're like most Bitcoin development is done with pre-existing wallets. Pre-existing like libraries. So for like JavaScript, Python, C, etc., it all already exists. So you never have to deal with these questions of like, okay, what exactly do I have to do to manage the bytes of a transaction or manipulate them, etc. So if you know something and I'm getting it wrong, let me know. I'm pretty confident in most of this, and I'll try to tell you if there's, something that I don't know. As Josh said, the goal is we want to get contributors working on this. And what that really means, both for Bitcoin and Lightning, is being comfortable, reading, writing, manipulating Bitcoin data structures. And in particular, using Urbit Hoon. But I think one end product that we'll probably get out of these, probably will end up being 2 calls, should also be some written documentation along with the video on how to just do Bitcoin development in general and make you a lot more comfortable with its various, primitives. So in terms of topics, we'll start off with basic stuff like just elliptic curves, wallets, and address derivation. Then the meat of it will be on just building and manipulating transactions, then signing them, locking, spending conditions, then looking at the code for how we currently do Bitcoin in Urbit. And maybe if I remember, I'll mention some of the improvements that we want to do. And then time permitting, I'll do just a quick overview of like Taproot and Schnorr and the motivations for that and some of the stuff that'll be added or changed. Okay.
Cool. Hey, you ready for slides, or you want to keep going?
Yeah, I'm ready for slides.
Cool. I'm going to drop off and let you take it over.
All right.
Yeah. Cool.
So the first one here, and let me see if I can, just in the background, pull up some of the things I'll be using as resources, is like elliptic curve basics. And this will become a little bit more important when we get to the schnorr stuff. But I find that it is useful in general to get. Yeah, you'll be like, for Black River software, like we should be schnorring at the end. So it's useful to know the basics of elliptic curves. And I should get like this is probably my favorite resource, and I put it here at the bottom. But just for those who, who don't know, let me see if I can find a decent picture down here. The basics of it are that you have some curve defined, that looks like this. That's in Bitcoin's case, y squared equals x cubed plus 7. So it's the symmetric kind of thing. And the important thing about it is that it has this operation, this point addition and then multiplication operation. Okay. And the way it's usually explained or that you show is you have 2 points on the curve. You have P and you want to add Q to it. And you can do it in either order, it doesn't matter. It's commutative. So you find a line that goes through them. It'll always go through exactly 1/3 point. So you find that third point. And once you find that third point right here, you flip it over the x-axis. You basically, essentially, it's y value, you turn it negative. So it goes to there. And that's a point addition. And that seems kind of weird and maybe, non-tractable, but you don't have to support many operations here. Even calling it addition is probably more of a metaphor than anything. And the important point is that if we have a point P and we have a point Q, we can do this operation called addition that gives us another point R. Okay. And then you could easily imagine that, from R, you could add R to P and do exactly the same thing, end up here, flip that and go here, and then add that to P. Okay. So whenever you're talking about Bitcoin addresses, both public and private, what you're really talking about is, and I can show it back here. I should actually have this written out in the thing. But what you're talking about is you start from some point, you add it to itself once, and I'll show what that looks like. And your private key is how many times, and then you add it to itself again. And however many times you do that addition operation is your private key, and where you end up is your public key. So it's this very kind of like tactile thing. And so let's say we start with, this point P, and that we can call that like sort of adding P to itself, like just 0 times, multiplying it by 1. Now we want to add it to itself, which you actually sort of in some ways can't do, because unlike when we had Q, we can't sort of tell where to draw the line. So by convention, it's always a tangential line, and we take the one place that spits us out. So in this diagram right here, that takes us to here. We would flip that over and get to this point. So 2P, adding P plus P is tangent line. You end up right down here. That's 2P. 3P is you add P to this point. Okay. So now we're into kind of normal elliptic curve from the beginning. Okay, so you go PP, that would give us, I think they'll show right here, it gets us to this point, that's 3P. And then 4P would be you draw a line between those, you intersect around here, you reflect that. The point is, you can do this operation as many times as you want, like millions, billions, quadrillions of times, and it's completely unpredictable where you'll end up. So if I tell you that we're gonna do 20P, you don't really, know from that. There's not much relation just looking at it between that and 21P, okay, or 22P. And so what that lets us do is that if I just show you a random point on this curve, you know where it is, but I can keep how I got there from P as a secret. And there's a lot of ways to then use it. And as long as I can show you this point and tell you I know how to get here, but you don't, but you can't know, you can use that as a public and private key. And so it's extremely like mechanical. When you see these numbers like, 3p, 2p, that's literally all it is all the way down. There's nothing more complex than that. And we're going to look at like this site in a little bit for looking at, keys and experimenting with them. And I'll show, what all this means. But when you look at like a Bitcoin public, let's say public key first, literally all it is 32 bytes right here, which are, when we see this number, by analogy, when we see this number 3p, that's like start at p and do this operation, add it to itself 3 times. This is a really big 32-bit number. So it's saying whatever this number is, 256-bit number, whatever this number is, do the operation to p. Well, it's called g, but we'll keep calling it p for now. Do the operation to p that many times, and then the front thing is 0.3. I forget whether it's 0.3 if it's positive, 0.2 if it's negative, because this whole thing here is the x coordinate of the point. So I'm going to back up a second, kind of make that a little bit clearer. But basically, this is a number. It tells you how many times to multiply by p to get to some point. And then to represent a point, we need an x and a y coordinate. So this whole number is, take back my previous explanation. This is not the private key right here is the one that tells you how many times to multiply it. The private one, this is a big number that's the x coordinate. And then as we can see here, if you know the x coordinate anywhere here, you'll know that you could be one of the 2 y coordinates. And so it's something like, I think, 0.2 if the y coordinate's positive and 0.3 if it's negative. So that's literally all that, a Bitcoin public key is. And then the private key over here, if you translate this number to like, just normal decimal, would be how many steps you need in order to, how many additions you do to get to like this point. Okay. And you can see like when you actually write them out in practice, the numbers are much bigger in their x and y coordinates. Now, the key thing that makes all of this work is that if I told you you have to do this 3 times p, we can do this pretty quickly. But if I tell you it's 20 quadrillion times p, it actually does take a fair amount of time to walk through each of those additions, right? And just do this to 3p, then we draw the line between 3 and 3p, and now we get 4p, etc. And we keep doing that 20 quadrillion times. That takes 20 quadrillion steps. And so it would seem like if I just give you a random point and how many steps it takes to if I tell you start at p and do 20 quadrillion steps, it would seem like it would take you a really long time to do that computation, even if you're the one who knows what that private number is, that it's 20 quadrillion steps. But it turns out there's something really cool we can do with elliptic curves. And this takes, probably you'll have to rewatch the video here a little bit, but it's very cool. And the property here is that if I say that we need to do 10p, it turns out that that's equivalent to doing 4p plus 6p. Okay, so as long as let's imagine that we just have a point, just 2, I'll just forget about everything else on this and just assume this is the 4p point and this is the 6p point. All we have to do is add those together, see where they end up, which would be like here, and that would be the same as 10p. So you can do this huge shortcut. If we pre-compute 4p and 6p, we can get to 10p really fast. Christian Crawford's asking, clearly repeated additions are not how one derives the public key because that entail tracing. Yeah, exactly. So that's not how you, this is the answer to your question. This is exactly what everyone thinks when they first look at elliptic curves. They're like, okay, what advantage am I getting? So the advantage you're getting is that you can pretty quickly see how if we just split 20 quadrillion and start, compute it as 10 quadrillion p plus 10 quadrillion p and then keep dividing that by 2, you can do that in log time rather than linear time. So whatever the log 2 of 20 quadrillion is, you can do it in that, and it's much faster. So this entire huge 32-bit, 32-byte, 256-bit number here, you could do in, I think it would be 256 steps, rather than 2 to the 256, which is a much, much, much bigger number. And so, yeah, as they're showing here, if you want to read the article later, you can calculate with like very few, and you can even actually, what you actually do in practice, and I think for people who have seen stuff in Ethereum, they do stuff like this for things, you could just pre-compute 2 times p, 2 squared times p, 2 to the third times p, and divide any addition into those and do it very, very rapidly. So that's elliptic curves. And these are used all throughout Bitcoin in ECDSA and Schnorr. So we've seen addition and what it means to add a point to itself with that. Just real quick, refreshing. It's like we use the tangent line as the start to kind of kick things off. Multiplying just means if you have 10 times p, that's doing it that many times. And then we had this distributive property where in Bitcoin and in elliptic curve cryptography from now on, the thing we've been calling P, we'll refer to it as G, which is a starting point that's agreed on by convention. As they say here, it's the point with X coordinate here, Y coordinate here is called G. And you do all, like literally a Bitcoin private key is just this number times G. Okay. And in order to do stuff fast, if you know the private key, we can do it fast because our final public point, CG, is the same as, we can keep dividing it into this A plus B times G, which equals AG plus BG. So what that lets us do is sign and encrypt. I'm not going to go through the ECDSA signing algorithm that Bitcoin currently uses. I'll go through the Schnorr one later. But I will show you that if we go to like zoos.hoon, and you're in I think it's the SecP core. I think someone's no, and you're in like the SecP core, and you go to ECDSA raw sign. What you do is you hash whatever message you want to sign and pass the hash as an atom. Then you pass your private key as an atom, which is literally just that big number of multiplications, number of steps, and it returns you a value of R, S, and Y, which you can use, which you can pass to someone and say, this is my signature. And if they have your public key, meaning that like kind of final point that you got to at the end of it, they can verify that. At the end, when we look at Schnorr, we'll actually look at the actual verification algorithm, because Schnorr is like much, much more elegant, and ECDSA was derived from Schnorr, but done in a really awkward way so as not to violate Schnorr's patents. So if I look at like the ECDSA like wiki, and you like look at the at the signing on it, it's actually like fairly complicated in terms of what it does relative to Schnorr, because they basically had to hack it up. So that's like for signing. You hash your message and sign, you commit to that hash and sign it and produce this RS value that lets you verify it if someone knows your public key. For encrypting and decrypting stuff, we actually don't need to do this in Bitcoin because you're not encrypting data. Just as a real quick aside, in Urbit and in Lightning, you do need to encrypt and decrypt. And so it's not immediately obvious. Like, it's kind of obvious looking at this once you get it, how, okay, we could use it to like make a public key and kind of find a way of using my private key to kind of prove I know how to get here, but you don't. For encrypting stuff, what you do is you use, and I could go into this more later off band, but essentially what you do is you each know each other's private key, and so you can use that to create this like special point that only you two know how to get to. And then you use that point's value to make a symmetric key and encrypt data. So just real quick, like in Urbit right now, the reason that comets can't talk directly to, or planets can't talk directly to comets right away, is that until the comet gives the planet its public key, the planet actually doesn't know what point to meet it at. So that's a separate topic. I'll do that off band or in the next session when we do like Lightning and we actually have to do encrypting. But it's just a little preview that you can use this math to create a secret point that like the two people who know each other's public keys can create to sort of rendezvous at. Schnorr is implemented in the upcoming Taproot upgrade. Time permitting today, we'll look at exactly how it works. It's a lot cleaner and simpler, although it still uses the exact same elliptic curve. It wasn't used by Satoshi because the patent didn't expire until 2008. So people didn't start, it wasn't sort of quite, out in the wild at the time he was writing this. It has a huge problem we'll look at in the very next section about signature malleability. And that I'll go over that problem then, but essentially you can change a signature and still have it be valid, like an outside party can. And Schnorr's algorithm is a lot simpler. So next thing, BIP32 and key derivation. This is how your mnemonics work whenever you're making those 24 or 12 word passphrases. The way they work is we can actually, I'll tell you it and then we'll show you using like this site. So let's imagine we have a 24 word mnemonic, like one of these things everyone's familiar with. And the end goal we want out of it is this like BIP39 seed, okay? So the way that mnemonics work in BIP39 is you generate, if it's a 24 word mnemonic, it generates a random 256-bit number. It makes a checksum at the end of 8 bits. So now we have 264 bits. It makes 24 11-bit words from that because 264 divided by 11 is 24. So that's where that sort of magic 24 word mnemonic comes from. From those resulting bits, we can make 24 11-bit words. 11 bits is the number 0 to 247. And if you look at, I bet I can find it. There we go. If you look at BIP39, it actually defines the word lists, like in English and others, that map those things from 0 to 2047, although this has like, an off by 1 thing, because it starts at 1, not 0. And it maps all of those to words. You translate those numbers into words, and that gives you your mnemonic. And from that, it can generate a seed. If you add on a passphrase, what it'll do is it'll, essentially combine the passphrase with that 56-bit number to make a totally different seed. And so that's what it means to have a mnemonic plus a passphrase or a mnemonic with no passphrase. But notice that this mnemonic will always generate the same seed. What it does with that then is it combines them with a few other numbers to make like a path. This thing right here. So it literally BIP84 is just like saying I want to use SegWit type addresses, and those just generate like a private key that can generate all the addresses in the count and a public key that can generate all of them. And you can see those here. So this is our sort of path, and then we just increment it up from 0 to 4 billion something. And for each of those, it gives us a new public key and a private key. And we'll see in the next section how public keys are turned into addresses, because Bitcoin itself, like at the sort of raw blockchain level, it doesn't care about addresses, and those are just like sort of a convenience for wallets. All right. The resources here, if anyone wants to look, are the math behind elliptic curve cryptography. And I should also add in a thing for, just as I look for it now, would be to do encryption with a meeting point. I should add a resource that gives a diagram of that. Okay. Any questions through that part before I go to this is really the real meat of the presentation coming up, which is transaction structure, because this is what you really need to know to write a wallet. Everything up to now was basically to sort of demagic elliptic curves and deriving addresses. If people have questions later about this, I can go into more detail. It's a really mechanical process, and everything just deterministically derives from this initial seed you get in that mnemonic process. For this section right here, I have, and I want to actually edit this, so I'll put it for later. I have two reference transactions that I'm going to show you guys and pull them up here. And what this is how we build transactions, which are like sets of bytes. So this is from BIP 143, which shows how to sign SegWit transactions. But this is what a signed transaction that's on the Bitcoin blockchain looks like this and is like, this long right here. Okay. And similarly, if we go to the bottom of this article, here's another like example fully signed transaction. So it's a thing of hex about this long, and we have to know exactly which hex goes where. So what I'm going to do is I'm going to actually walk you through the transaction here in its unsigned and signed forms and show you exactly what we do in order to generate it, hash it, sign it, just manipulate it any which way we want, and how that works, because our current Hoon code actually has to do almost all of this. So the transaction always has the following parts, and then with some minor changes between exactly how they do depending on if it's SegWit or not. So the first thing it always has is a 4-byte value called N version. And this value is in little endian. Little endian means that if the number is 1, like let's say there's 4 bytes and the last ones are 0, so this is the number 1, it puts the smallest byte first. Okay, so if you put this number, if we did like, this number in Urbit like that, it would look like that. And there's implicitly, 4 3 0 bytes to the left of that. But in Bitcoin, they're represented like this, which is called little endian. Then we go next to transaction in. This is, and on the blockchain, the stuff about transaction in, transaction out isn't written. All that's written is the numbers, the hex. And so when you look at the thing at the end of the day, it just looks like this. So then we have what's called a compact size number that shows how many transactions inputs we have, which are, and a transaction. And so here we have 2. So now we know when we're parsing it that we should expect to parse exactly 2 things, and they'll look like, they'll look like this. The next thing is 32 bytes, and it's the transaction ID in little endian order. I wonder if they used a real one for this. I'm actually not sure. If we went here, okay, they did not. So if you this would be like if you took a real transaction, you could actually go look it up, and we're going to be spending all of the money from it in here. The next thing here is which index it is. So a transaction can have multiple outputs. And this is saying from this transaction, I want to use the first output, 0. Then we have a byte here that I'll talk about. When the transaction is unsigned, it will always be 0, 0. And then we have here this like what's called a sequence number, which is again 4 bytes, and I'll explain that in a sec. All inputs put a sequence number, this 4-byte sequence number at the end. So we have same thing down here, another transaction spending the second, like index 1 output of this one. Then we say we have 2 transaction outputs. This is the value we want to spend from it. So for the inputs, you always have to spend the whole thing. For the outputs, you actually choose how much money goes there. So this is a number in little endian. And if we converted it and flipped it, we could actually see how many like Satoshis it is exactly. So it would be like, because it's in little endian, we would actually, if we were writing it in Urbit, we would just, and yes, I could like, I could swap the bytes. I could like, actually I could show an example of doing that, but I'm not going to like flip, I'm not going to flip them all right now, but whatever, let's do it. So we could actually like manually flip them around like inside Urbit. And then we have like 06 as the next one. and we could translate it to a decimal. So this is 112 million Satoshis, so a little over 1 Bitcoin. Okay, so we have to flip the number to get its actual its actual value. So any code working with this has to know that all of these values through here are little endian in the transaction. Christian Crawford says you spend the entirety of the specific UTO, but not the whole. Yeah, that's correct. So you have to spend the entirety of the input here. But you only spend the one at this index, not every input in the transaction. In fact, that wouldn't even be possible because we're going to look at output locking scripts in a sec, or it wouldn't be possible in most cases because you might not even be able to unlock the other, output UTXOs of that input. Okay, so we have the value. Then we have here exactly what we're getting to, which is called a locking script. And this is a series of opcodes followed by a public key. In fact, it's easiest if I go into here, I'm going to choose a random transaction or a random address. I'm going to go to the transaction for it. I'm going to go to the details, and I'm going to compare these two things up here. So right here, we see that this locking script is 1976A9. You're going to see this all the time, this 1976A9 with 88AC at the very end. And the reason is, if we look at one of these addresses, and you look right here, and they show you the script pub key, we see 76 A9 followed by with 88AC at the end for one of these addresses starting with 1. The reason is that 19 is the number of bytes, so it's 25 in hex, and this whole thing here is 25 bytes. So here's 1 byte, 2 byte, 3 bytes, 20 bytes, 24, 25. And so the 19 at the front is saying that, and they just omit it here in the script pub key, but it's actually just for printing purposes. Yeah, Drew Hamblin. The reason the explanation is clear is because I had to actually learn all this in order to write it. And most people, if they're writing a Bitcoin wallet, they literally just take a pre-existing library and they do it. And so they actually never have to do this. They don't have to write a library that says, for example, if I can I'll make this stuff bigger and give a quick preview. But if we look at bitcoin.hoon, and I was going to show this in part 4, but literally here, we have to take a address and return what's called a script pub key, which is literally just this string of hex. And so it has to do all these conditions to see whether it's base 58 or base 32, do all this stuff. And literally, if you just notice here, it's actually saying concat some bytes. And then those are going to be 3, we're going to start with these 3 bytes of 76A914, and then put the 2 bytes at the end of 88AC. Okay. And then finally, we do. Actually, wait. That makes me wonder. I think you can get away without putting the byte count at the front because this is doing it, and in my implementation here, I also leave out the byte count at the front of the 19. The 25 in hex. So I think that's not that's currently optional, because otherwise it wouldn't work. This thing wouldn't be in the blockchain here. And then finally, you do this end lock time. Christian L, this is not rolling our own crypto for the reason that rolling your own crypto is if you come up with a new one of these, either in terms of an elliptic curve or the signing mechanism for using this elliptic curve and the numbers that it generates. So if you look at the whole Schnorr white paper by Maxwell and Polstra, all these Peter Woyle, all these based core devs, they actually had to go ahead and submit this for peer review. It got someone actually found a huge problem with it. Actually, on 2 cases, and they had to fix it. And this is the part where you actually are rolling your own crypto, coming up with a way to use this elliptic curve to do multi-signatures. That's rolling your own. Making ECDSA is rolling your own crypto. Making Schnorr and how you use the elliptic curve for Schnorr is rolling it, which is why Klaus Schnorr like patented it, and no one could use it for a while because that is like sort of a really valuable process. This is not rolling your own crypto. This is, yeah, we're adding adapter signatures. Absolutely, Jack Ken's this is like using someone else's crypto to like munge some bytes together and do stuff with them. Pretty much. There's nothing really. This is super mechanical. This is more like working on a car. End lock time, I'll explain in a sec, but every transaction has to have it. So that's our transaction. Let me use this to stay on track. When we see a transaction ID, like up here, and this is in Little Indian, it is a very specific thing. The transaction, in fact, I should change this thing. It's double SHA-256 hash, the above fields. So you take, to hash a transaction, if your inputs are SegWit, you actually would take exactly this SHA-256 hash it 2 times, and that is your transaction ID, no ifs, ands, or buts. If one of the inputs is not SegWit, and I'll show in a second what that means, your transaction ID is actually exactly this, except you have to put its signature instead of the 00 here and hash it in a specific way, and that is your transaction ID. And this is actually the whole reason we needed SegWit, because the transaction ID now changes based on how you sign it. Okay? And so the transaction ID is now, in the old version, like Satoshi's vision, so to speak, the transaction ID depended on what signature you ultimately use to unlock that input. Okay? In the current, in SegWit, it no longer does that, and you always zero this out if the input is SegWit, and I'll explain what that means. So we set up here, when we looked at our outputs, they had this thing called a locking script, which is this set of hex, which also some of the bytes map to opcodes. So what this is this is a script where you give it inputs and it has to evaluate to true at the end. So I'll go through real quick, like just in super simple detail, what those look like. So for the super simple one, to sign a like old version input, like basically if you want to unlock this input, what you would do is we would point to this transaction ID. We would say, I want to unlock the second one in it. So we would put like, 01 as our thing here. Okay. And then we would say, I know, and then in this slot right here, we would insert a program that runs against this and evaluates to true at the end. Okay. So what the program would be, and I have to like remember this real quick, is we would put our public key, the signature, and our public key. Okay. Then it would take this, it would run opdupe on the public key, so create a duplicate of it. It would hash that duplicate value to 160 using hash 160, which is you run SHA-256, then ripemd 160. If I go to, we're going to look at this again in the end, but if I go to, I think I put this in here. Yeah, hash 160. Literally all it does is you pass in a value, you SHA-256 the value, you run ripemd 160, which is another hash function that outputs a 20 byte value, and that is it. Okay. And any Bitcoin quote unquote like address, like this thing here, if I run it, if I copy the value and run like a base 58 converter that I should be able to find online. So here's like our, decode address to, yeah. Okay. So this base 58 value decodes to this. This is a 20 byte value starting with 0, which is, 1. 1 in base 58. So point being, I would say, let me just go back here now, where we were. Oh, come on, man. There we go. So it would hash that. It would get like, this thing right here, and it would say like, whatever comes out of hashing the public key needs to be equal to this right here. D4, is it? Like, yeah, it is. So notice we see here D49084, and here just stripping the leading zero, D49084. Okay, so it's running a very mechanical program. Then it says equal verify, so that makes sure that these bytes are equal to the hashed public key. As long as they are, then it removes that, and now it runs check sig and checks whether the public key that was given matches the signature. Again, we could go into more detail on this later, but the key thing is that we pass it two values. It puts them, the sort of interpreter, the Bitcoin core interpreter, when it's checking to see whether a spend is valid, like basically you've given it a new transaction, like this whole like mush at the end, and it wants to see whether it's a valid spend. It checks the signature that you gave, meaning notice here in our final transaction, we spend one SegWit output, so we put a signature here. It actually just takes that signature. There's a signature here, and there's a public key here. It puts both of them on top of the stack and then runs this program against it. Okay, and if it evaluates to true, it's a valid spend. So that is how spending works in sort of original Bitcoin Satoshi's version. You make your output be an unlocking script, and if anyone wants to spend that, they have to provide this like a program, meaning just like a set of data that when you put it at the front of the stack and then run the unlock script, it evaluates to true, and then they can spend it. Okay. So, and actually, so that's Bitcoin script. Just as a quick preview of what it looks like in Lightning, this is another type of script. This all just turns into hex at the end, but it's some different opcodes. You insert some different hex values here, and it does like some other stuff. Okay. Addresses and spending scripts. So we're looking here at this output. I think the clearest way is to look in the mempool. We see this address, and we see this like script pub key. Okay, and so we have to think about like what does it mean to send Bitcoin to an address? And it really just means that you say, I want to, how would I say this? You say in your output, so sending to this address really just means make this program in hex. Jack, I did not mention sig hash. It's the next thing coming up. And it's definitely like one of the more annoying things in here. So not annoying, but like hard to find information about. It's actually really simple. So basically it just means make this program and make it be the unlocking script in my output. That's what it means to like send Bitcoin to an address. Now, we have a few different kinds of addresses. We have base 58 ones, which either start generally, if you see them on the blockchain, on the main chain, they'll start with a 1 or a 3, which is their version. And these ones, if it starts with a 1, your wallet will treat that as like, make this program, like for the output, where the hex value this decodes to becomes the thing we insert into here, and we kind of do that around. And my code does like actually exactly that pretty much. It's literally just saying, if we have an address and we want to make it to a script pub key, it's pretty much doing that. We could also, if we go back to like a recent block, if I look for a 3 signature, what these look like, and I'll just open the transaction and show what they're like a lot shorter and or a little bit simpler, and all they are is like hash 160, push these bytes, and this is called pay to script hash, and I'll explain that in a sec. Then there's base 32, which is those BC1 addresses that you've seen, and those use SegWit. And they have some sort of specific parsing rules, but all that they are, if we go back to like, one like this, This is a different format where each thing here is a base 32 value. So each of these things represents a number from 0 to 31. And the first number is always, and then the thing before the one is a human readable part, and the rest is a number. And what that number evaluates to in hex is these bytes right here. Okay. So the script pub key is like op0, then 32, and then the exact same thing like as there. So those are the two different kinds of addresses. The only difference between them is the newer ones are base 32 for a few reasons, and the older ones are base 58. But at the end of the day, they're just a wallet convenience, and they all turn into hex at the end. So when we have our two script pub key, we take an address, it doesn't matter which of the two formats it is, and we can turn it into a hex value. Okay. And I'll go into a little bit more detail about these types of things in a sec, but I have to get to the rest so that it makes sense. Also, there's two kinds of when you want to lock scripts based on time, it can be locked by the funder or the sender. So if you want to do a timeout and say this transaction can only be spent, let's say 10 blocks in the future, you can either have that be the funder doing it, as in Lightning, where he said that you make this output and you say, basically the op check sequence verify says it can only be spent X blocks or time in the future, which is this number that you insert here and translate into hex. So that's the funder imposes that restriction. You can also have the person making the transaction impose it. So if I go here and I choose a really high lock time, that means I'm saying I'm making this transaction and presumably I'm signing it, but I don't want anyone to be able to use it until X time in the future. I don't want it to be able to be posted at all until then. So either the funder or the spender can impose that. If the funder is imposing it, it's done with op check time lock verify or op check sequence verify. This is an absolute time condition. This is relative. So this is at this block in the future or at this time in the future, this output is spendable. And this is after this many blocks or time, it's spendable. Now, when a transaction has an end lock time value, it's always enforced sort of by the interpreter. So if you have an end lock time, this is an absolute time value or block value, and it must be in the past. Otherwise, the transaction can't be posted then. So if this thing is a block that's in the future, this transaction just won't be accepted until enough blocks have happened that it's in the past or enough time has passed. And that's always checked, and this was built into Bitcoin pretty much from day one. Sequences were not. They were Satoshi originally imagined them being used in a different way, and it turned out the way he wanted, just has a lot of issues and is subject to DDoS attacks. So essentially, we had this whole extra field kind of available, this sequence number at the end of each at the end of each thing. Okay, so each input was using this 4-byte value, and it's not really doing anything. So what they did in Bit. Was it 69? I don't know. I actually should have that in the resources here. They redefined that to say, okay, if you set n version as 2, and this thing meets a few criteria, such as the first bit is 0, or sorry, isn't 0. Yeah, so I think the first bit has to be 0. I need to check again. But anyway, if n version's 2 and some conditions are met, the interpreter will treat this as being an absolute lock time. And then depending on how you code it, you can either be a relative lock time. And depending on how you code it, it can either interpret it as blocks or time, depending on how big the number is. Okay, so what it means is that if this condition, op check sequence verify, is on the output that you're trying to spend, let's imagine one of these that you're spending had an op check sequence verify. In order to spend it, you would have to commit to a sequence here. You would have to make the version of your transaction be 2. And your sequence you would have to commit to would have to be, you know, this amount of delay in the future. Let's say it's 3 blocks. Okay. And so it'll only evaluate and work if this input has already been in the blockchain for that number of blocks. Okay. So that's like, so it's a little bit confusing. With lock time kind of makes sense. There's 2 confusing things, which is what does sequence mean? And the answer is that it's been repurposed in some specific ways. And the other confusing thing is, why is there also op check sequence verify and op check time lock verify if we have like end lock time and end sequence here? And the answer is that it's the difference between having the funder impose the condition when they make the output, or having the spender impose, like commit to, you know, the condition and saying this can only be spent, you know, in this, you know, after this time. So those are those. That was in about 10 minutes. Like that took a long time to like actually lock down and figure out. It's just so badly explained in terms of what's magical and what's not and what's by convention. Like, I don't know, what was the thing in Star Wars where many of these creatures died to bring us this information? Bothans or something. It's pretty much that. So now let's get to sig hash, as Jack asked about. And what sig hash is when you sign a transaction, let's say I'm signing in order to kind of spend this output, I also need to commit to a few things when I sign. So I need to commit to at least one input saying I am signing for this input, and I need to, you know, I'll explain the exceptions to it, but generally you need to commit to at least one input and one output. Usually what you do when you sign a transaction is you actually commit to all the inputs and the outputs, which means that this signature is only valid to spend this input if the input gets spent in a transaction that also spends this other input and these 2 other outputs. Okay? And that's the opcode sig hash all, which is represented by the number 1. I should put it to do here. Resources. To do sig hash codes. There's a good like codes. There's a good thing for that. And the other one is in sequence bit. Okay. So that's called sig hash. So what you do when you're signing is you actually include a little code that says I'm committing to, you know, either all of the outputs and inputs or maybe just one of them in my signature. So the basic things you can commit to is you can commit to none of them, which is you say, if you have this signature, you can actually just go ahead and spend any input that matches my pub key, and you can send it anywhere. And that's used mostly for like miners to collect dust. You just throw that out there because maybe the amount left in the UTXO is too small, and miners can go and kind of bundle those up if there's free block space that they're not using, and just make it, you know, sweep all those up. That's not used very often. There's also sig hash all, which is the most commonly used, which says you can only spend if it's done in this exact configuration. There's sig hash single, which says you can spend. I commit to this input ID, transaction ID, and to this output, you know, with its like all its values. But anything else can happen in the transaction. There can be other inputs being spent, other outputs created. I don't care. I just care that like my input that this signature is used to spend exactly this input, and this output needs to be here. And then there's also anyone can pay, which you can kind of think of it as crowdfunding, which is you sign the input and maybe it's not even enough money to fund the output that you're signing for. Like the input is 1 BC and the output BTC and the output is 20 BTC. And that says, I'm fine with other inputs coming into this transaction. They just need to go to this output also. So that'd be like, you know, I'm fine spending my input as long as some other people can be found to crowdfund this. So the way sig hash works mechanically is when you, let me just see where exactly it went here. You bundle up all of the information in a specific way in order to hash it. It's different from the hashing for that you do. It's different from the hashing that you do for transaction ID. It's this exact format here. You have to put the stuff in this order in this way. And so what you do is you hash the previous outs, you hash the sequences used, and you hash the outputs that you're committing to, and you put them into like this data structure. Here's this pre-image here is like broken down into its component values here. And then at the very end, you put a 4-byte value of the sig hash, which here is 1 for sig hash all. Okay, so let's walk through mechanically what happens. So we commit to the sig. We put all these into a long pre-image. We put the n hash, the sig hash at the end. We commit to it by hashing it. We use ECDSA to sign this hash, and then at the very end of it, so that's like you see this signature here, like 30422. That's like exactly this thing here. At the very end of the signature, which is a signature right here, and then we put the pub key after, we put the 01. So in 1 byte, I know it's really dumb, but they do 4 bytes here to represent sig hash, but then at the end of the signature, you put 1 byte representing which sig hash you used. So what that means is that when the Bitcoin kind of validity, like, interpreter goes to see whether you properly were able to spend the input, it will check we'll show how it does it for SegWit, but it'll check the signature against the pub key, and it'll also make sure, and when it gets the hash value that the signature is committing to see if it did it proper, if it committed properly, it'll look at this and be like, oh, okay, you told me you're going to do it for sig hash all, so I'm going to go ahead and do it for that. For sig hash single, it would go and do just for the first input and the first output and hash those. So that's sig hash. Real quick, now we really need to get into SegWit in a second. But once we make that signature using sig hash, you can put it in 2 places depending on the input that you're spending. If the input is an old, what we'll call like Satoshi style input, meaning it uses like those, it's one of those addresses that, like, just writes a full script here. Then what you do when you make the final transaction is you generate the signature and you put it right after you have the transaction ID for the input, the index for the input. You put the signature right in there and then the sequence. And that's going to need to be hashed to make the transaction ID. If the input you're spending, so here's the first input they have is an ordinary P2PK, meaning it's this script pub key. If it's a SegWit input, which we'll talk about in a sec, then what you do is you put that, you put it afterwards in what's called like a witness program. Okay. And PSBTs, real quick, this is like a format for collecting signatures. So you could like easily imagine that, like, maybe these inputs here came from different people and you need to collect signatures for each one. PSBT, which I've linked to, is BIP 174, and it's just like a separate data format for holding signatures or for holding transactions and collecting the signatures that you'll need for each input. I use it internally, so I have it implemented here under BIP 174, and it's really just a hex munging thing to to make a compatible format that you can send to hardware wallets, other like programs like Wasabi Wallet, and collect signatures. Saying that's wallet signing, pretty much how it works. Like if you have a cold card or something, what you do is you create one of those PSBT hex structures, send it to it, and it fills in the signature and sends it back, and then you can construct a full transaction out of that. I'm going to talk about any pre-val and no input later. Any preval, just real quick, it's needed to make a thing in Lightning that doesn't exist yet called L2. And currently, you're not able to construct a signature that says, basically, I'm committing to these outputs, but I don't care which input I'm spending, as long as it corresponds to the public key, as long as it's spendable by the public key that's signing this thing. And so that's not currently implemented in Bitcoin. Now that Taproot's in, it might come in, and we get into Lightning and L2 in the next session. We'll see why it's useful. But just for now, know that you can say, I want to just spend one input and one output, or an input and an output, and then have other inputs come in. But you can't just do a signature that says, I'm signing for this pub key and this output, and any input spendable by this public key can go to it. You cannot currently do that. There's some proposals for how to do that called like any preval, like sig hash any preval, or it was originally called no input. Okay, let's get into SegWit, because this is where like I had to kind of lay all of the groundwork here in order to talk about how SegWit works in all ways, because this is by far, in my opinion, the most confusing thing for how to construct a Bitcoin transaction. So the motivation for SegWit was like twofold. And I can put it to do like you could read the like block size wars book, which is really, really good about this whole thing. But essentially, the first reason was that transactions IDs were malleable. And the reason is in BIP 0340, they talk about this. This is the one that implements Schnorr signatures. ECDSA signatures, like if I have your signature right here, let's say I'm a miner, and you've given me this transaction, and one of the inputs is signed for in this is an old style input, and you've given me this signature where you commit to a certain hash with your pub key. Even if and let's read it here, what they say, a third party without access to the secret key can alter an existing valid signature for a given public key, okay, into a signature that's valid for the same key and message. What that means is that if I'm a miner and you give me this transaction, I can change this signature into a different value. It will still be valid for spending this in all ways. I can't steal anyone's money. Like, you did in fact want to spend this input. But what I can do, because our transaction hash is basically in pre-SegWit, or if you have an old style input, even in SegWit, because our transaction hash includes the signature, like puts the signature into the slot right here for an old style input, I can change the final transaction ID. Okay, so what that means is that if you give your transaction to a miner or to anyone before it's been like confirmed on the blockchain, they can change what transaction ID it will produce. In the original sort of Satoshi version of Bitcoin, that didn't matter because people weren't doing, weird stuff with transactions stored off chain. But in Lightning, it absolutely matters. And I'll go into the specific attacks when we talk about Lightning next time. But basically, it basically like breaks Lightning if you can't know until the transaction's confirmed that what the final transaction ID is. Lightning's not workable. Okay, so that's the first reason that it was needed, and people knew about this problem, and there were different approaches to solving it, and SegWit was the one that was eventually done, because it also does a little trick that lets you effectively increase the block size beyond 1 megabyte. To an average, if you look at an average block now, they're like maybe 1.5, 2 megabytes, something like that. Okay. I won't talk about exactly how that works, but I will talk about exactly how you do SegWit and what it means. So all that SegWit is at its heart is this. In the old style, to publish a transaction, the transaction was everything here except there's the witness part isn't here. The marker and flag aren't here. We have everything else. And instead of this 00, we need to provide an unlocking sort of signature script right here. Okay, that's an old style Satoshi's call it Satoshi's vision Bitcoin. Okay, SegWit is if one of these inputs is a SegWit input, and we'll talk about what that means, you cannot sign for it by putting it in this slot. This slot must be 0, 0. And you must put it in this sort of extra space we create here called the segregated witness, hence SegWit. Like we make this what's called a witness program. A witness program is pretty much exactly the same or very similar to these script programs, these old style script programs. They're just segregated and put out here. And then there's one minor difference in how they're interpreted. Okay? So that's a witness program. And to make a SegWit transaction, all you do is you take your original transaction, any fields that are old style, any inputs that are old style inputs, you get them signed for and include their signature here, but you know sometimes there won't be any. Then you put a witness program at the end, which is you say how many. I need to check like the exact format of it. So you say number of stack items for we know before we see the input, the witness program, how many inputs we have, which is here too. So for the first one, we say how many items will be on this in this witness program, and we say 0 because we signed for it here. It's an old style. For the second one, we say it will have 2 items, and we then proceed to put those 2 items there. The first one is a signature with sig hash appended, and the second is a public key. Okay, that's all. So that's all SegWit is if you're spending an input that's SegWit, you need to do this. And if you want to make your transaction SegWit compatible, regardless of what your inputs are, you need to put this marker and flag, and upgraded node since 2017 will know what to do with it. So to make it so a legacy transaction, you can see a clear diagram like right here. It just looks like this, which is, if we scale it up, this is just a diagram of what we saw. Version, count of inputs. Here's an out point. All this stuff. This is probably a worse diagram. Probably I actually like this a lot better. So an old style transaction is this with the signatures filled in. Okay. And a SegWit transaction is that with the things filled in if necessary, and these couple extra fields and the witness program if necessary, with zeros if they're old style. To hash a transaction in SegWit. So if you're submitting a transaction to the blockchain and it's SegWit, all you do is you fill in any of the signatures that are for old style inputs. You take out the marker and flag and the witness program, and you go ahead and hash it. And that's your transaction hash. So if both your inputs are SegWit, it will be totally non-malleable because the signatures will always be outside it and never be included in the hash. So I can probably find an on-chain example of what a sort of fully non-malleable transaction would look. Yeah, here we go. So this transaction is if you looked at its hex, because the inputs and the outputs are all, or actually it's just because the inputs, but because both inputs are SegWit, that means that there's no way you're not allowed to put a signature in here. And so there's no way to change the transaction ID if you're a miner or someone else who has access to it. Okay, and so transaction ID is not malleable if all the inputs are SegWit. And you set the SegWit inputs, they set the script sig, aka the signature field right here. You set it to a 1 byte with a value of 0 in order to hash the transaction and get the ID. All right, we are actually almost through here with, wait, did I not put in size? That's really bad. Oh no, okay. Finally, whenever you see a wallet and it has a transaction size calculation, like when you see in your wallet, it'll say, actually you can see right here, how many sats per V byte. And the question is, what is a V byte? Like right here that says this transaction is 200, I'm sorry, that's wrong. where does it show the size here? Yeah, its virtual size is 208.5 V-bytes, and its size is 372 bytes, and the weight is 834. We are going to learn exactly what that means, how to implement it, because I had no clue how to do this when I first did the wallet, and the implementation in the wallet is currently correct, but not like extendable. And so that's something that's going to need to be done by me or a contributor. Okay, we're going to look at exactly how you can calculate this. So if all of your basically the way that V-byte calculations work is you add up everything in your transaction that's non-witness and multiply it by 4. You then add in everything that's witness, multiply it by 1, and divide that whole thing by 4. So let's start with the easy case where it's a fully old style transaction. In that case, you have no witness components, right? We don't have the witness program. We don't have the marker and flag. We have our signatures in here. So we add up how many bytes this whole thing is without that stuff. We multiply it by 4 and divide it by 4, and it's just how many bytes it is. So if you make a transaction that's fully old style and submit it, essentially if it has no new style inputs, and it's just not even SegWit, doesn't have these fields, it'll just be its size in V bytes will just equal its size in bytes. And so it would be, I could probably even find one of those real quick. If we look at all the transactions and like, because a lot of people still use, yeah, this would be like, so if we look at this one, it has an old style input and output, and you actually see size and virtual size are the same. Because it doesn't, this is someone who's actually not using SegWit as it shows right here. Now, that's the easy case. The slightly more complicated case is when it's SegWit. So they're kind of highlighting here. It has that marker and flag, and then the witness program at the end. And those all count as SegWit. So the way you would calculate like this transaction's V bytes is you add up all of we take the raw byte count and if it's non-witness, multiply it by 4, and we go through the whole thing doing that. They're going to show what's called, here's the running total weight is the number they get when they multiply non-witness bytes by 4 and witness bytes by 1. We go all the way down and we get a number, in this case 542. In the case of that all SegWit Chad transaction, it was 834. And you divide that number by 4, and that's the V bytes. So the real size of this transaction is 218 bytes, but the V byte size is only 135. Because essentially we basically pay, what this really comes down to is we pay a quarter price for all of our witness program signatures because they're segregated and they're not technically in the transaction size. So that's how they were able to get around the 1 byte megabyte block size thing without having to change it in code, was by segregating the witness outside and then kind of counting it as cheaper for V bytes. Same here, it's 372 bytes total. We actually have a lot of signature data because we have to spend 2 different inputs. Whereas here, it's only spending 1 input. And so it's 372 bytes, but you only have to pay for 208 bytes in the thing, because a lot of those bytes are located outside in the witness program. In the spending, notice how the signature takes 72 bytes and the pub key takes 33 bytes. So it's like 105 bytes there just to spend 1 input. And that's a big part of, this is a 218 byte transaction. So a lot of the transactions, like actual size, is spent just in the signature and the pub key to spend it. Okay, so that gets us, so that's how you do size. Currently in my code, I don't have that implemented in a fully general way, so I need to find that. I literally actually just found this today when I was looking for a clear explanation for that part. That's the best one I've seen. So finally, how do you spend what's called like hash scripts? So if you have one of these, both in old style and new style, if you have one of these like scripts that's kind of long, like one of these lightning ones here, you actually, and if we looked at like the output on chain, those are push bytes 20. What you would see for when you made this into a transaction is all you would see here is, 32 bytes, which is a hash. And so the way you spend one of these scripts is on chain, it makes a 32 byte hash. And in order to spend that output, you have to include your witness program, which is the full script. Then also it'll hash it for you and check whether it matches that hash. And then you have to include all the data for the program. Real quick, one more thing with SegWit and spending it is, I should have put that here, like SegWit. So real quick, difference between Satoshi transactions and SegWit ones, we saw that the output locking conditions for Satoshi ones, as we call them, were like, push this onto the stack, then do it. For SegWit, they basically said, all right, you know what? We do this operation so many times, we should just build it into the interpreter that if you see 20 bytes, if it starts with op0 and you see 20 bytes, just know the witness program has to be take the signature, take the pub key, hash the pub key, make sure it matches this, then make sure the signature works for that. So you can make the output locking script a bit smaller. 22 bytes? Yeah, 22 bytes instead of 25. Okay? And then same if you want to spend like one of these more complex outputs, which are a 32 byte hash, it says if you see something, let me try to find one. That's like, I bet this is one. If you see something that, no, it's not. If you see something that's a 0 and then a 32 byte hash, just take the witness program, hash it, and make sure it matches that hash, and then make sure the witness program is like a script that then evaluates to true, like this one with the right stuff filled in. So that's how you spend hash scripts mechanically. What they mean is the extra spend goes to the spender, not the funder. This is nice for Lightning and other stuff. Basically, you can get cheaper, cooperative closes. And then the problem is that like you have these it's not locking scripts. You get large like unlocking scripts because you have to include the full script whenever you unlock. If you want to spend the script later, you also have to store it because you have to know the script so that you can later hash to it and show that like the script you're posting that evaluates true that you maybe know some secret for or can sign for. You have to also know the script so that you can show that it hashes. All right. I'm going to go quickly to the Urbit Bitcoin implementation and then try to blow through Schnorr, but maybe end Taproot in like 5 minutes and then go to the happy hour. Urbit Bitcoin implementation, this is going to be a lot faster. Division of labor, we currently do everything in our library except signing. That'll be implemented soon. I guess I could also say, I could also talk a bit about like multi-sig. We actually also don't implement multi-sig or paying to like hashes and storing that. So we have Bitcoin utils.hoon. It's only a few files that implement most of the stuff that I showed you. We have Bitcoin lib/Bitcoin utils.hoon, which is like this file. It implements, so the motivation for it, the reason it's split out into a separate one, is that we also have some sub-libraries in here, like BIP174, like for partially signed Bitcoin transactions that needs to depend on it. And so but we also want to include BIP174 at the top level. So in order to avoid a circular dependency, we make this Bitcoin utils library. What it handles is it has this like blop core, which is basically just bit byte manipulation. They just say if it's bits, they basically just both wrap it depending on whether it's bits or bytes. And this is just basically doing interop. Urbit's core tools are a little bit annoying for leaving zeros. And so this is just stuff for doing bit byte manipulation in that way. It also has hashing with some also leading zero stuff handled. It has this type that I use all throughout, hex B, like hex for Bitcoin interop, which is just like Urbit has a bytes type. Oh man, I need to. Can I? Sorry, I don't know how to zoom this in, but so like Urbit does have a bytes type, but it interprets the second thing as just an atom, not hex. So hex B kind of lets you say how many bytes are in your thing, and then print it as hex. So I use that all throughout the code. Compact size is the other thing here. And this is this Bitcoin specific type. The easy way to say it, and it's used for things like saying how many transactions inputs do we have here? And it basically says if the value is only 1 byte and if the first value is less than 252, I think, just treat it as a number. And then if it's greater than that, treat it as telling us how many bytes there are in this thing. And then like read the number. So it lets you use big numbers, but if your number is under 252, you can represent it as just in 1 byte. So I just have a thing here for encoding and decoding them. Bitcoin.hoon. Bitcoin.hoon is the main one. It exposes BIP 173, BIP 174, also BIP 158, and Bitcoin utils are all exposed through it. There's also a SIR file that it exposes and includes, which is just all these Bitcoin and they make them bigger, Bitcoin and transaction types are all exposed there, and partially signed Bitcoin, stuff like that. And then BIP implementations, we have these are exposed through Bitcoin.hoon, and they have ones for block filters, which are basically these things that are now included with Bitcoin transactions, where when you download a transaction from the blockchain, it also gives you this like thing that only takes about 1% or 2% of its size, and it's a data structure that lets you check a list of addresses against it and return which ones of them are in there quickly. So if you get a new block, you can determine whether you care about any of the addresses that are inside it. When we say address, I actually don't mean like the address in this form, but rather it lets you check the script pub key and see whether they're in there, just to be fully general. BIP 173 is base 32, just the implementation of this, this base 32 structure that translates down. And then BIP 174 is partially signed Bitcoin transactions. As more are added, we have the format to put them in there and then expose them through Bitcoin.hoon. All right. Taproot basics, and then I'll move into happy hour and try to eat a little bit. We can do a live stream of me eating. Any questions so far before I get to Schnorr? Let me give like 10 seconds to see if anyone types anything. Essentially is less interactive than I thought it needed to be. Or people are wusses. Two. All right. Krishnell is typing. All right, this is not good radio, so I'm going to move through this and then we'll go to the happy hour. All right, Taproot. I'll give the motivation and the very basics, and then I'll give some resources for people who want to self-study or ask me more on the Urbit chats, because I've been getting pretty into this lately. Motivation is that for things like Lightning or for multisigs, you want more privacy when, let's say you have a 2 of 3 multisig, but you can get everyone to agree, like all 3 people. It lets you spend that in just like one thing that looks like a normal spend. It also lets you do more fee efficient spending of complex scripts. Like, for example, let's say you have a script on your locking your output that has like, let's imagine 4 different OR conditions. So right now, that would hash to some 32 byte value, and then to spend it, you would have to paste the entire script. Okay, and then but you won't. But maybe you only have to like successfully execute one of its branches for that to work. And so what Taproot does, and let me see if I can. Oh, because I was smart, I put the Bitcoin Ops summary of Taproot. Bitcoin Ops is like a really good site, by the way, and a lot of my links that I have here are from there. Where my thing is like is pretty good for like just really getting this mechanical feel, but they go over like just everything happening in Bitcoin development and how to do it at mechanical levels. It's a great site. Um, so basically, Taproot says it lets you put one of your Aura branches on one side of a Merkle tree, and then your other ones in other parts, and then essentially like when you want to spend them, post the Merkle path that you want to spend from, along with just the script that you're spending, and so that saves a lot of space. Okay. Um, and then Taproot also enables Schnorr signatures, which I'll talk about really briefly, and then show my favorite resources for them. And this also enables additional functionality, like Jack mentioned, with adapter signatures, which let you do things like point time locked contracts. Detailed summary, I will not go through all the way right now, so I'm just going to like skip to the resources and point you to the good stuff. The Bitcoin Ops summary is great. It's very readable, just like executive summary that shows how all of it works, and I'm happy to answer questions about it. They have a great workshop on it, which looks something like this, where they just have a sequence of a few pretty straightforward videos where they take you through. I would especially recommend the 2.0 one, just about Taproot itself. You can even skip Schnorr signatures initially, although it's a good intro on them as well. Here's the BIPs about Schnorr signatures. And then in order to understand Schnorr signatures, if you just combine it with just quickly reviewing this elliptic curve document that I linked in the other one, and then go directly to Taj Dryja's talk on it. He's one of the original Lightning paper guys. And then go through the first half of that, and you'll get Schnorr pretty well. It's an extremely simple algorithm, and he does a good job of like showing how, even verbally comparing it to ECDSA and why it's simpler because of the patent considerations. Rene Picard's walkthroughs are really good for Schnorr signatures, then multi-sig, and then adapter signatures, although I think he goes on too much about how it's like a crazy result with them, whereas actually I think it just follows really straightforwardly from the math. And then Andrew Polstra, one of the people who did Schnorr multi-sig for Bitcoin, has a really good presentation about Schnorr and the different stuff they went through doing it and other things they can do. So that's also highly recommended. The paper I've linked to here, if you're kind of a paper guy, you can check that out. I found the above videos pretty sufficient. I can talk more about Schnorr maybe in the Hangout, but I think we're at a pretty good time here at an hour and a half. So I'm going to take any last questions, and then I'm going to okay. Let's see. I'm going to post the Mike. If you're watching this, we should post the Hangout link and switch over to there. Here's the backstage. So I think actually I think I have it in my thing. So I could probably people who are on. Yeah, here we go. I'm gonna switch over to that. I might. I just don't know. Is it bad if okay? He had to leave the string. There's the happy hour link. Oh, that's a good. Yeah, Jake, that's a good question. Yeah, I think a question session is a good idea. We can schedule it maybe kind of informally, and I think also most questions I could probably handle just in chats, and then I think watching it again and looking at the resources would get there. But if it's really necessary, we can do a live Q&A, or maybe I'll even do one sort of off band, just informally in a video call, not as a scheduled thing. Also, call to action before we finish. We have new bounties up for this thing. So we need people to maintain the Bitcoin wallet. I actually want to, I want to get that so I can screen share that. I wonder if they're probably up here now. Yeah, I did it. So here, if you go to it, there's the Bitcoin wallet maintenance. Essentially, if you know JavaScript front-end logic well or Hoon, we can use you. And we have this kind of ongoing thing for a few months where we need to do ongoing improvements, both that we already know and bugs that arise. And I'm going to be taking over kind of like lead on maintaining it and making it a community thing. So that's like, really important if you or anyone you know has either JavaScript or Hoon skills, we can make it work. All right. I'm going to switch this off now and move over to the happy hour stream. So later, guys. It's been real.